So hello and good morning to everyone. Today's lead code question is through 3286, which is find a safe walk through a grid. So basically in this question we are given an M cross and binary matrix grid. So binary matrix grid means it has either 0 and 1, right? And with that we are also given an integer named as health. And what we need to do is we'll start from the upper left corner, that is 0 comma 0, and we have to go to the lower right corner, that is m minus 1 comma n minus 1. So we have to move from 0 comma 0 to m minus 1 comma n minus 1. And the steps that we can do is we can either move in the up direction, we can move in the down direction, in the left direction, and in the right direction. So these are the four movements that we can take, right, to an adjacent cell. And we can take these steps as long as our health remains positive, as long as our health is positive, right? So it is given that the cells I comma j whose value is 1, these cells are considered as unsafe, right? So whenever we move to that cell whose value is 1, our health will reduce by 1, right? So we try to avoid these cells whose value is 1, and at the end we have to return true if we can reach the cell m minus 1 comma n minus 1, and our health should be greater than or equal to 1, right? If our health is less than 1, then we have to return false, right? That means we have reached the cell, but we haven't reached the safe cell safely, right? So this is a question. So let's see the examples. So in the first example, this is a grid that is given to us, and we have to start from this cell, and we have to reach the, this is our destination, we have to reach over here, and we are having a health of 1, right? Our health is 1, right? So if we take this path, then here at this point only our health will become 0, which is less than 1. So we can't take this path. So if we take this path, and then from here again we go to this direction, again here our health will become 0, so we can't take that path also. So we go to the downward direction, and then if we go here, if we go here also again our health will become 0, so we can't move in that direction. So here we move in the up direction. Then if we again go here, our health will become 0, so we go in the up direction, and this is the path that we'll take. So if we'll take this path, if we'll take this path, so we can see we do not reach to any cell whose value is 1. That means we do not reach to any unsafe cell, right? So what will be our damage here? So our damage is basically 0. So whatever health that we have initially, that will be our final health, so our final health will be 1 if we go by this path. And as per the question, if our health is greater than or equal to 1, then we have to return true. So we have written true over here, right? So let's see the next example. So in the next example, this is our grid, and our health value is 3, right? So no matter which path we'll take from 0 comma 0, we have to reduce the health by 1, either here or here, right? And then if we go here, then again our health will be reduced by 1. And then if we take this whole path, then the damage that we get is 3. So if the damage is 3, what will be our remaining health? Remaining health is current health minus damage, that is 3 minus 3 is 0, which is less than 1. So we can't take that path. Let's say we take this path. Again in this path also the damage is 3. Even if we take this path also, then the damage is 3. So in this example, no matter what path we take, our damage is greater than or equal to 3. That means our health will always be less than or equal to 0. So there is no path such that we can reach safely from 0 comma 0 to m minus 1 comma n minus 1. So we have to return false as the answer. right? So let's see the constraints. So m, which is the grid length, n, which is the number of columns in the grid. So these m and n should be lesser than or equal to 50. It can be up to 50, and 2 is less than or equal to m cross n. That means we can't have a 1 cross 1 what you call grid over here in the question. Also our health value can be up to, it will be less than or equal to m plus n. So in the worst case it can be 100 when both m and n will be 50. And as we know, the grid is a binary grid, so the values that will be present will be either 0 or 1. So let's move to the approach part. So basically what we can do is we can think of every cell. So we can think of every cell as a node in the graph, and then as we know, from a cell we can move either in the up direction, down direction, right direction, and the left direction. That is, we can move to the four adjacent cells. That means this cell is connected to its four adjacent cells. So if this is a node of the graph, then these are the four nodes. These are the four nodes with which this node is connected, right? This is the first thing. And now as we know, if we move from this node to a cell whose where value is 0, that means that particular cell is a safe cell safe cell, right? Because that cell do not reduce our health, right? If the value is 0, then our health will not be reduced. But if you move to a cell whose value is 1, that means that cell is a unsafe cell, and our health will be reduced by 1. Our health will be reduced by 1. So now what we do is, now instead of thinking in terms of how much health is remaining, what we do is, now instead of thinking in terms of like how much health is remaining, what we think is that when we move from 0 comma 0 to m minus 1 comma n minus 1, how much damage has been done to us, right? So we have changed our thinking point. Earlier what we were thinking is that how much health is remaining, but now what we are thinking is that how much damage has been done to us, right? So when we enter a safe cell, then the damage that has occurred to is 0, right? But when we enter an unsafe cell, then the damage that is done to us will be 1. So now we have converted our current problem into a different problem. That is, we have to find a path from 0 comma 0 to m minus 1 comma n minus 1, such that we have to minimize the total damage done to us in the path, right? So we have to find a path from 0 comma 0 to m minus 1 comma n minus 1, such that the total damage should be minimum, right? And then once we get the total damage, and if that damage is less than our health, that means we have reached safely. So then we can return true, else we can return false, right? So this is the overall flow. Now the question is like how we'll find the damage, right? How we'll be finding the total damage from the path 0 comma 0 to m minus 1 comma n minus 1. So as we know, to find the minimum distance or minimum damage between two nodes, that is a source node and the destination node, we we use Dijkstra algorithm, which will give us the shortest path in a weighted graph. But the thing is that here we have only two edge weights. So either the edge weight is 0 when we move to a safe cell, or it will be 1 when we move to a unsafe cell, right? So we can use Dijkstra over here, like we can use Dijkstra also over here. But as we know, when we move from a node having distance d, and if the edge weight is 0, then the distance will remain the same, that is d only. And if the edge weight is 1, then our distance will be d plus 1, or we can think distance as damage also, right? So when we move from a to a cell whose edge weight is 0, then our damage will be d only, else our damage will increase by d plus 1. So we can see over here is that we have only two possible distances, right? If we move from a cell to neighboring cells, then we have only two possibilities, that is either, if here the current damage is d, then either the damage is d or it will be d plus 1, right? So now what we can do is, now as we know in the Dijkstra algorithm, we maintain a priority queue. We maintain a priority queue to find to find the to find the node with the shortest distance, and then process that node whose distance is the shortest one. So here we have only two possibilities, either d or d plus 1. So we can maintain that using a dq, right? So instead of using Dijkstra over here, we'll use 01 BFS algorithm, 01 BFS algorithm, and use a dq to maintain the distances, right? So whenever we get a edge weight with edge weight is 0, then what we'll do is, then we insert the neighbor at the front of the dq, because the distance, if the distance is d, it will remain d only. So we'll process this node first, right? We'll give priority to this node first, because the distance hasn't increased when we move from one node to the neighboring node. But if the edge weight is 1, if the edge weight is 1, then we insert this new node at the back side, at the back of the dq, because our distance has been increased by 1. And then what we'll do is, then we process this uh, later, right? So suppose if you have two nodes, one is with distance d and one is with distance d plus 1, then we'll give priority to the node with distance d and we'll process it first, right? So this is an example that if our current distance is 5, and then we have to move to a safe cell whose weight is 0, then distance will remain 5. And then if you have to move with the unsafe cell, then weight is 1, so distance will become 6. So now out of this 5 and 6 cell, we'll give priority to this cell and we'll process it first. So that's why we'll push it in the front of the dq, right? So basically it's similar to Dijkstra's priority queue, but as we know in Dijkstra's priority queue, the time complexity is big of log v. But here, when we know either we have to insert in the front or in the back direction, so that will take only big of one time. That's why we are using dq over here, right? So if you see the overall algorithm, so what we'll do is, we'll treat every cell is a node of a graph, and then we'll assign edge weights, right? To the We'll assign edge weights. So edge weight is basically equal to the value of the destination. Suppose we are currently at this node, and then we go to this node. So if this node has value 0, then the edge weight will be 0. If this node has a value 1, then the edge weight will be 1. So depending on the destination, we decide our edge weight. So if the edge weight is 0, if the safe cell, then edge weight is 0, as the edge weight is 1. And then we'll apply 01 BFS from 0, 0 to compute the minimum damage, to reach every cell. And then once we get the damage to reach n-1 comma n-1, so that is our the minimum damage, to reach n-1 comma n-1. And if our damage is less than health, that means we have reached our destination safely, and then we return true, else we have to return false, right? So this is the whole approach. So now we'll try to understand this approach with the help of an example. So we have taken this grid and our health value is 1, right? So basically, as we have discussed, that the cost of entering a cell is basically equal to its value. So if the cell value is 0, that means it is a safe cell, and the cost to move to this cell is 0. But if the cell value is 1, that means it is a unsafe cell, and the damage or the cost will be 1. So initially we maintain a distance array, where this will tell us the distance of at any point I comma j, will tell us the minimum damage that is required to reach the cell I comma j, right? So Let's see. So initially our distance array will be like this. All the cells will having the value infinite, and we have reached 0 comma 0, so its value will be 0. So now we have pushed this cell, as the damage is 0, we have pushed this cell into the DQ, right? We have pushed the cell 0 comma 0 in the DQ. Now what we'll do is, now we'll pop out the cell from the DQ, that is 0 comma 0, its current damage is 0, and then now we'll process it. Now we'll see who are the neighbors of these cells. So for 0 comma 0, the neighboring cells are 0 comma 1 and 1 comma 0. So these are the two neighboring cells. So 0 comma 1 has a value 1 and 1 comma 0 has a value 0. So it is a safe cell and it is a unsafe cell. So this cell will give us, our current damage is 0, so this will occur a damage of 1. So at 0 comma 1 we add what you called, our damage will become 1, so we update that to 1. But 0 1 at 1 comma 0, it is a safe cell, so our current damage will remain the same, so we have updated that to 0. Now 1 comma 0, 1 comma 0 is a safe cell, so we'll push it in the front direction, in the front direction of the DQ. So we have pushed 1 comma 0 in the front direction, and 0 comma 1, 0 comma 1 is unsafe and it has a distance 1, so we'll push it in the back direction, right? So after processing 0 comma 0, after processing 0 comma 0, this will be our distance matrix and this will be our DQ. So now again we take the front element from the DQ, which is 1 comma 0. So we have taken 1 comma 0. Now at 1 comma 0, the current damage is 0. So what are the neighboring cells of 1 comma 0? So the neighboring cells of 1 comma 0 is 0 comma 0, 1 comma 1 and 2 comma 0. So these are the three neighboring cells of 1 comma 0. But as we know, 0 comma 0 is already we have processed that. Still if we process that, it will take, at 1 comma 0 the damage is 0, and at 0 comma 0 we have value 0. So 0 plus 0, it will again become 0. So now at 1 comma 1 we have a value 0, at 2 comma 0 we have a value 1. So again our current damage is 0, so 0 plus 0, it will be 0. At 1 comma 1 the value will be 0, and 0 plus 1, it will be 1. So at 2 comma 0 our damage will become 1. So we update these two values, that is this value and this value in the distance matrix, right? And now as we know, here at 1 comma 1 we have 0, so we'll push it in the front direction, in the front direction of the DQ, and then we push 1 comma 1, sorry, not 1 comma 1, this is 2 comma 0, this is 2 comma 0 in the back direction of the DQ. Similarly then we process 1 comma 1, update our distance matrix and update our DQ. Then we process 2 comma 1 and then update our DQ. So now at this point, when we take the front element from the DQ, so that is 2 comma 2, having a damage of 0, and as we know 2 comma 2 is our destination. So that means we have reached 2 comma 2, that is our destination, with a damage value of 0, and as we know our health is 1, so 1 minus 0, what is our remaining health? Remaining health is 1, and as we know, since remaining health is greater than 0, that means we have reached safely, so our answer is true, right? So let's move to the code part. So in the code part we have taken a vector, a matrix distance and a DQ, right? And then we are initially putting, so distance of 0 comma 0 is basically whatever value that the grid 0 comma 0 is having, and then we are pushing 0 comma 0 in the DQ, and these dx and dy are basically to move in the up direction, left direction, right direction and down direction. And then we take the front element from the DQ, and we check if it is our destination, and then if it is our destination, then we check that the damage is less than health, if the damage is less than health or not. If the damage is less than health, then it will return true, else it will return false. And then after checking this, we'll process all the four neighbors, so if the neighbors are not present in the grid, then we skip it, else we take the value of the new neighbor, and then check if the current distance plus the edge weight, that is the value of the new neighbor, if that is less than the value that is already stored at the neighbor, then we update the distance of the neighbor. And then we do, if the value of the neighbor, if the edge weight is 0, then we push in the front direction, else we push in the back direction. And once we do this for all the cells, we get our answer. So if you see the time complexity of this approach, so the time complexity is big of m into n, right? So that's it. So I hope I'm able to explain the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.